Hello guys, this is going to be a video discussing some basic principles of electronics and radio in particular using the popular and cheap CF210SP DIY radio kit which you can get online from sites like AliExpress and Amazon. I got mine from a site called robu.in. They've got some cool stuff if you're into DIY electronics, and I'll put the link in the description. So anyway, there's already a bunch of videos on the YouTubes about this kit, but they tend to focus more on the assembly and gloss over the circuit functioning. I think the way to get the most out of this type of kit is to analyze and try to understand the circuit as you build it. So that's what I'm going to focus on with this video, and I hope you learn something as you follow along. So I won't really be getting much into the actual kit assembly in this video. There's a bunch of really good videos by other YouTubers that you can follow for assembly tips. I'll link to some of them in the description. Instead, I'm going to talk about some basic electronics concepts which I hope you will find interesting as you build this kit. Or even if you're not building the kit and just want to learn a little bit about how a radio receiver works, I'm a huge fan of radio kits and I would love to make more videos like this if you guys are interested. So I hope with this one that I can introduce some basic concepts that we can build upon later with more advanced kits. Also, I'm still learning most of this stuff myself. I do my best to ensure what I say here is accurate, but if you're serious about learning electronics, please do pick up some good books as well, instead of just taking some random guy on YouTube's word for it. So anyway, let's carry on. Okay, so the CF210SP is a AM/FM receiver kit. So as you already know for sure, AM and FM are two ways by which we can superimpose an audio frequency signal onto a radio frequency signal in order to transmit it over long distances. So what we are actually, so let's talk about AM first. So what we are actually doing, trying to accomplish with amplitude modulation and even frequency modulation is basically we have an audio frequency signal like this, and we need to transmit this over a long distance, but we can't simply transmit an audio frequency signal. Audio frequency range is considered between around 20 hertz to 20,000 hertz. So the reason we can't just transmit audio signals, there's two reasons. I mean, there's a whole lot of reasons, but for a simplistic explanation, two would suffice. So first reason is that if all the radio stations transmitted audio signals, all the broadcasts would clash against each other, right? But that isn't even close to the biggest problem that we have. The biggest problem is audio signals between the audio in the audio range would not propagate very far. We need to cover any significant distance, we need a higher frequency signal. So that is why to we need to combine this with a high frequency RF signal in order to broadcast our radio stations. So what is done in amplitude modulation is we have a carrier frequency which could be the AM broadcast band is somewhere between 500 and something kilohertz to around 500 and something kilohertz to around 1.6 or 1.7 megahertz, something in that range. It depends on which part of the world you are around, but that's generally where most of the country's AM broadcast bands lie. And so what we do is we combine our audio frequency signal. We have an audio frequency signal over here. We combine that with our RF high frequency signal to get something like this. So what this basically is that the the, the audio the variation of the audio signal has varied the amplitude of the RF signal. So basically, as we can see, the audio signal is basically riding on the RF carrier. So this way we can transmit the same information, we can transmit this information stored in the audio signal over a long distance by basically modulating an RF signal to basically carry the audio signal. So in our radio receiver we can tune it to receive this RF signal, and once we have received that RF signal we need to detect it by getting rid of it. So basically we are only left with the amplitude modulation, and once the high frequency element of this is removed we are left with an audio signal that we can pass to our audio amplifier and we can hear the output at our speaker. So now there are some issues with AM. So first of the biggest issue is that it's very susceptible to noise. That is because uh, various forms of noise, interferences, atmospheric conditions, they mess with the amplitude of the signal, right? And because the amplitude is what is transmitting our information, it causes distortion, it causes noise, and that is why we later came up with FM, frequency modulation. But AM, the frequency ranges allocated for AM, they propagate higher distances. That's why AM is still used for shortwave broadcast, and uh, although AM broadcast band is out of its way in many countries, there are still a couple of AM broadcast stations around. And since AM is, it's much simpler to, you know, build an AM receiver than it is to build an FM receiver, AM is very much alive for hobbyists, in my opinion. So with FM, just like with AM, what we have to do is we have to superimpose an audio signal onto a radio frequency signal. So as you can see, we have a audio frequency signal here, and in green we have a RF signal. But what is happening here is that instead of altering the amplitude of the RF signal, we are altering the frequency. So when the audio signal, the amplitude of the audio signal increases, the frequency of the RF carrier increases. Then when the audio signal starts to go down, the frequency of the RF carrier goes lower as well. And once the audio signal starts to increase in amplitude in the opposite direction, the frequency again increases. So basically, this is how the audio frequency information is basically used to modulate RF radio frequency to to change the frequency in accordance with the audio signal variation. And what this allows us to do is this allows us to get an radio frequency signal that transmits our audio information, but without the amplitude of that signal mattering, of the RF signal doesn't matter here. So basically the noise doesn't affect our end result, because when we demodulate this signal, we will be converting the variation of this frequency into an audio frequency signal. So if any noise has affected the amplitude of this RF signal, it won't really matter much to us. And so that really is the advantage of FM. Now the radio that we are building is built around three integrated circuits. So as you probably know, an IC basically contains a slice of silicon which has been etched and doped to form various transistors. So basically they contain a circuit inside a small package, complete circuit. So we only need to provide the inputs and the outputs. We don't need to care about actually designing our exact circuit when we're using an IC. So that makes things more compact, and it also makes it cheaper because they can be mass produced. It makes it assembly easier, because say instead of needing like 10 transistors, we only need 3 chips. So so let's take a look at the chips used in this radio. So we have an audio amplifier IC, which is the TDA2822. We have this thing which looks like a transistor, but actually it's an IC. It's a TA7642 AM receiver. It's a tuned radio frequency receiver, and we'll talk about that later when we get to it. But for now, let's focus on the third chip, which is the CD9088, which is also known as the TDA7088. This is a FM receiver IC, and this is a super heterodyne type. So this is a bit of a shortcut AM front end, but this is a legit FM superhead receiver on one chip. So let's as we start building it, let's take a look at the circuit of each one of these ICs and how they fit into a radio and how they work. So here is the instruction sheet that is supplied with the kit. As you can see, it's not very useful. Even if you can read Chinese, you can try Google translating it, but it doesn't really get into much detail about how this works. And if you can see, this looks a little bit confusing right here. But what we have to do to analyze this is we have to break it into parts. So most of this stuff is our audio amplifier section. Over here is most of the AM receiver section, and all of this is the FM receiver section. As you can see, the FM section is built around the FM chip, and the AM section is built around the AM chip, and the audio amplifier is built around the audio chip. And rest of most of the rest of the stuff is just things like the power supply, volume control, and so basically to make this easier to understand, let's simplify this down to a block diagram. Okay, so here's a badly drawn block diagram of that schematic. So as you can see, we have three separate sections built around one IC each, and we have a separate FM receiver and a separate AM receiver, and the output of each one, either one, is switched to the audio amplifier. So we can use this switch over here to control if the output of the FM receiver or the AM receiver is going to the audio amplifier. And the power supply is not shown in this simplified block diagram, but basically both of all three sections are powered on at all times. So it is kind of inefficient in that way, because say we are listening to FM, the AM is still running, but it's not a big deal because these chips don't draw much current, so it's not going to have too much effect on battery life. But just just it's interesting that they did it that way, I guess, to save costs. And also you can see, let's go step by step now. So what is the job of the audio amplifier? The audio amplifier has to take the output, both of these stages, the receiver stages, are going to output audio signals, but they are going to be very low in amplitude and very low in power. So what the audio amplifier has to do is step up that signal enough that it can drive this 8 ohm speaker. So basically, it's the same reason why you just cannot plug in your smartphone to a 8 ohm speaker. Despite, nowadays with Bluetooth speakers, people have forgotten that every speaker needs an amplifier. Almost every speaker, unless you're talking about something with a really high impedance, which, like sort like the headset used in a crystal radio, something like that. But in most cases, you need some sort of amplifier to step up your signal enough to actually uh, get the speaker cone to actually move enough to produce sound. So, and let's go now down to the AM receiver. So you might notice that both of these receivers have a similar looking thing attached to them. So what this symbol over here and this symbol over here, it represents a coil or an inductor. And these symbols, this one and this one, they represent a variable capacitor. Now a coil is simply, literally just a coil of wire, and this is basically two metal conductive plates separated by an insulating, can be air or can be something else, but in this case it's just air. So this and this what these are tuned circuits. Yeah, LC, L for inductance, C for capacitance, LC tuned circuits. So the thing about tuned circuits is they resonate at a certain frequency. So basically they transmit energy back and forth between them. So at one point in time the energy will be stored in the inductor in its magnetic field, and then it will discharge into the capacitor. It will store that into an electric field, and then that would give it back to the inductor, and so on. So they get sensitive at a particular frequency known as the resonant frequency. So we will talk more about that later, but basically this is an important aspect of a radio receiver, is the LC tuned circuit. So we have a separate tuned circuit for AM and a separate one for FM, because they have to cover a different range of frequencies. So in the case of the AM receiver, it has to tune to a frequency between any frequency between 550 to 1720 kilohertz. It then has to amplify that, filter it, and demodulate it. So once we demodulate it, we are left with an audio signal. And the FM receiver has to tune into a frequency between 87.5 to 108 megahertz. Well, this particular kit goes lower than 87.5, but 87.5 is the actual low range of the FM broadcast band in most countries. So basically, this has to tune within that range to a station within that frequency range, amplify it, filter it, and demodulate it. So obviously, in case of the FM demodulator, we have to detect we have to convert the frequency variation into an audio variation. While in the case of the AM demodulator, we it's more about getting rid of the RF carrier and just leaving the AM modulation. So yeah, these are the three sections of the radio. Okay, so the logical way in which I like to build radio kits is start with the circuitry for the power supply to make sure that we have the juice that each section needs to function. And then we go backward from the audio amplifier to the front end. So that's how I'll be approaching this kit, the same way I approach even more complicated kits. So in the standpoint of getting good results in terms of the neatness of your soldering, etc., this is not the ideal way to do it. You would want to start with not paying attention to what section you're working on, but you start with the lowest profile components and work onwards to the bigger ones. But I prefer this way because you get to think about what you're actually building. So how the way the schematic relates to the PCB layout and things like that. And that's how I encourage you to build this if you're following along. Okay, so I've outlined over here the power supply components, but let's take this out of context from rest of the circuit, so it's easier. You don't have all this clutter in the background, so we can just focus on the power supply. Okay, so all electronic devices need some sort of power supply. The job of the power supply section of a electronic device is to make sure that all the other sections of the device get the right voltage they need, and the power supply also needs to be able to supply enough current for all those sections to function. So in this case, let's take a look at what voltages we require. We need 3 volts for the audio amplifier. We need another 3 volts for the FM receiver section, and we need again 1.8 volts for the AM receiver section. So let's see how all of this works. So let's start with the batteries. So we have two AA batteries connected to give us a total voltage of 3 volts. We have we have the switch over here, the on off switch, which is located in the volume control. We'll talk more about that later. And basically what this does, it switches the negative side of the battery to the ground rail. So all of these ground symbols you see are connected to the same circuit trace. So basically they all come to this point, and when this switch is open, there is no connection to the negative side of the battery, so there is no complete path for current to flow, and the circuit is turned off. So basically closing the switch connects the negative side of the battery to the ground rail, allowing the circuit to function. So we get 3 volts over here, and that 3 volts is directly supplied to the audio amplifier. C25 is the main power supply filtering capacitor, which it kind of stabilizes the power supply in the sense that uh, it makes sure there is no ripple. It makes sure we have a steady DC level here. So if there is sudden surge of current, if any of the chips draws a sudden surge of current, it it prevents the power supply from sagging down. And also if any RF radio frequency interference created by the receiver chips, it keeps that off the power rail, so we have a steady 3 volts at this end of the battery. We have two more filtering capacitors. We have C24 and C23, which basically help the same purpose, but these are located closer to the AM section to provide some additional filtering over there. And yeah, so let me see. Mm, yeah, R22. Here's R22. This is the current limiting. It's R722 ohms. It's not R22. Excuse me for that mistake. So it's this 22 ohm resistor is a current limiting resistor for the FM. So it doesn't really, because the 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 input impedance of the FM chip is high enough that this doesn't really if you think of it like a voltage divider, this doesn't really have any significant voltage drop across it to reduce the output to much less than 3 volts. So we are still supplying 3 volts, but we are, I guess, limiting the current little bit. Just it's hard to say why exactly we need this without knowing the internal circuit of the FM chip, but yeah, I feel it's a current limiting resistor. because I measured voltages and we are getting 3 volts at the chip. And yeah, so we have here, and you see this R9, R8 and this LED. This forms kind of like a, a voltage regulator for the AM section. So this chip, the TA7642, I believe it was, I might have forgotten, but this chip is known to require a steady operating voltage. So if you think about it, how they have accomplished this is, see, obviously this LED is also an indicator light for when the radio is turned on. But if you think about it, the the AM section is connected across that LED. Now the voltage across the LED will be very constant, more or less constant, despite little bit despite some small changes in current. So basically, we are using this as a way to regulate the supply voltage to the AM section. So it's a clever multi-purpose circuit. So to sum this up, 3 volts is fed directly to the audio amplifier and to the FM section via R7. The LED R9, R8 form a voltage regulator for supplying 1.8 volts to the AM section, and that's about it. Okay, so here's the back of the volume control potentiometer. So these three pins relate to the volume control itself. So we'll talk about that later. But for now, you should turn your attention to this cam over here, which is connected to the rotor of the volume control. So when the volume control is all the way down, we are essentially disconnecting this contact over here. So point B is separated from point A. Point A and B are the switch contacts. So they are not connected internally at all. So don't get confused they're not connected internally at all to the volume control. It just happen to be on the same housing. So it is this little cam thingy here that breaks this contact when the volume is turned all the way down. And so point A is connected to ground and point B is connected to the negative side of the battery. Ignore this plus sign over here, that is a mistake, I apologize for that. But basically this is the physical manifestation of the volume control slash on off switch that we talked about. Okay, so here's the power supply components all soldered onto the PCB and ready for checking voltages. I used an external battery holder for testing without installing the PCB into the case. So basically, the negative side of the battery is connected to point B of the volume, not the volume control, but the on off switch which is located in the volume control, and the positive side can go to any point which is electrically connected to where to the positive rail, basically to the main positive rail from which rest of the rails are created. So I use this resistor here just as a convenient point to add the alligator clip to. Okay, so once the power supply section has been assembled, what you have to do is check the voltages at all the pads where the ICs are soldered on. Look at the schematic and the PCB diagram and find the VCC pins to each of the ICs and make sure there is voltage there only when the switch is on, and make sure we have the right amount of voltage over there. So that is your homework for this stage. You can try to do that, and also you can, if you'd like, you can check the current draw. There should be a negligible current draw right now of this. If you'll have to connect your ammeter or milliammeter, maybe even microammeter in series with the external power supply at the board. So you can see how much current it draws, and then you can compare it after you have you build the rest of the components and see the total current. You can compare the current draw now with the actual current draw when it's completed. It should be negligible because there really isn't any load. And yeah, you could also measure the voltage drop across the LED and check it with the data sheet of an LED and see if it tallies up. And also you could try to work out how much current is flowing through the LED, by looking at the resistors around it and doing some KVL on that. So yeah, Kirchhoff's voltage law, for if you're not familiar with that. And so basically, yeah, that's what you can do now at this stage, just to play around with it. There's not much else you can do. If you can think of something, let me know in the comments. But I guess we can now finally move on to the audio amplifier, the fun part. Okay, so now we're getting started with the audio amplifier section of this radio kit build. Let's get on with it. Now, as you can see, I have highlighted the audio amplifier section here, which we have, as discussed earlier, is built around the IC TDA2822. So, with working with ICs, the first thing that you should do when you encounter a chip that you're not familiar with it is look up the data sheet for that. So just type the name of the IC space data sheet into Google and see what turns up. So let's do that now and let's see if we can figure out if we can learn anything about the 2822 IC that way. Okay, so here's the data sheet for the TDA2822 IC. So basically these sheets are just some information uh, about the chip, if you're designing a circuit with them, and it tells us right here what this is. This is a dual low voltage power amplifier. Notice that it says dual. So basically this one chip contains two amplifiers on it. So it is intended for stereo applications, or it can be bridged. I'll talk about bridging. It is what is done in this CF210 radio kit. It says here bridge or stereo configuration, and let's scroll down a little bit, and here we have the very important pin connection. Note the indexing pin, which marks the site with designates the site with pin 1, and then we have pin 1 output, pin 2 supply voltage, pin 3 which is the second output, pin 4 which is the ground, and then going this way we have pin 5 which is the second negative input, and pin 6 which is it's hard to see over here, so let's zoom in. If that's the negative or positive input, we have the second positive input, and we have pin 7, this the first negative input, and pin 8. Okay, so pin 7 is the first positive input and pin 8 is the first negative input. So as you can see, there are two pairs of inputs, negative input and a positive input for each of the internal amplifiers. So when you have a negative input and a positive input, basically what you're dealing with here is an op amp. So op amp is a very common type of amplifier circuit, which originally was designed to be used to conduct mathematical operations and things like that. But modern audio power amplifiers are very similar to op amps, and so I highly recommend this article on markhennessy.co.uk, op amps and introduction, to learn the basics about op amps. I find it very useful to be familiar with op amps when you're just getting started. So there's basically, op amps are very versatile, but let's not get into that right now. I suggest you go and read that article, but let's scroll down and focus on how the TDA2822 is used in a radio. So this is the internal circuit. It might seem confusing at first, but it is a very traditional audio amplifier or very traditional op amp kind of circuit. So since this is a stereo, basically the entire circuit is repeated twice, so you only need to understand one side of it. Actually, when you're just using the chip, you don't need to understand the internal circuit at all, but it's good to be aware of it. And I think eventually you'll get the hang of, you'll find this sort of circuit very similar. You have your differential input pair, your differential amplifier, which is what gives it the op amp functionality, because you have the negative input and a positive input, and basically what is happening is the difference between these two inputs is amplified, and you have your regular audio output stage, your push pull audio output stage, and all of this is just to ensure phase inversion, so that both of these transistors are conducting out of phase. But yeah, so if you're interested in that, you should look up push pull audio amplifiers or class B audio amplifiers, and you'll understand what all of this is. So we have some absolute maximum rating, so this chip can go up to 15 volts, yada yada. We're just running it at 3 volts, so most of that isn't really relevant to us. The max power dissipation, I believe this is not the max output power delivered to the speaker, but uh, the max power that can be dissipated by the chip, so I'm not sure about that. I'll have to, you can correct me in the comments if you know what that is. But let's scroll past all of this to the test circuit, and the stereo test circuit is right here. So RL, this is a test circuit. In an application circuit, this would be our speaker over here, where RL is there right now. And as you can see, it is very simple. It's just two amplifiers. The input for the first amplifier, we have an input resistor to set the impedance, and one of the inputs is simply grounded. So since we're amplifying the difference between the inputs, and one is at AC ground, so that's the difference that we are amplifying. And the other channel is basically the same. We have our plus V plus, which can also be often also called VCC here at pin 2. But if you look at our circuit, if you look at our CF210 radio kit, this is not what's going on here. If you look at the schematic, what's going on is more like this. So what this is a bridge configuration. In a bridge configuration, basically, instead of using this chip which contains two amplifiers for a stereo application, we are using it as a mono application, but each amplifier is connected together in such a way that they are receiving an input signal which is out of phase. So the negative input of the first amplifier is fed to the negative input of the second amplifier, and the positive input of the second amplifier is grounded. So the end result of all of this is that we are basically getting a much higher voltage swing at the output and much more power delivered to our load than if we would have with just a single amplifier, just using just one of these two amplifiers. And anyway, we have one speaker in a radio, and we have a mono FM chip there. We don't have FM stereo, so it would have been a waste. So we can use the other amplifier, combine them and get more output power. So this is called a bridged amplifier circuit, and that is what's happening in the CF210SP. Okay, so here is the TDA2822 circuit as used in the CF210SP kit. So we have our plus 3 volts entering the chip at pin 2 at the top, and over here we have the main ground of the chip, which is at pin 4. This is just connected to the ground rail. The signal is fed into pin 7 via the volume control, and C19 at the input shorts high frequencies to ground. So this improves stability, and it also this is not a high fidelity amplifier, so we don't really need a lot of high frequencies. I doubt that little speaker used in this radio can cover the entire audio frequency range. So we can improve stability by getting rid of some of the higher frequencies, and FM has a pretty decent frequency response, but I believe the AM can't do high frequencies at all. So generally with a small radio like this, you don't have the entire audio frequency range anyway. So this basically, yeah, and this also, I guess it could also, short out any radio frequency interference, things like that to ground. So that's what this C19 is for. And the inverting input of the first amplifier, which is pin 8, this is connected to the inverting input of the second amplifier at pin 5. And you can see here the speaker and the headphone jack are connected between both the outputs of both the amplifiers. So basically between pin 1 and pin 3. So basically both the amplifiers are driving that one load, and both of each of these outputs, basically this output is a mirror of this output. So basically uh, you know the voltage swing that we're getting here is twice the voltage swing of each uh, each output alone. And an interesting thing about this configuration is that the maximum voltage swing, thanks to the bridge configuration, is actually more than 3 volts. We're getting almost twice the supply rail voltage swing here. So that is one of the advantages of using a bridge configuration. So you can get a high output with a low voltage power supply. So that is pretty cool. And we have C26, C 27 over here, R11, R12. So basically these are Zobel networks. So what these do is they counter the inductive effects of the speaker voice coil. So basically they improve stability. It's basically compensating for the non-linearities caused by the inductance of the speaker. So you'll find a Zobel network like this with a small resistor and a capacitor in series going to ground across the speaker in most of these small IC based amplifiers. It's a very common thing. And you can see here non-inverting input of the second amplifier is just tied to ground. So this is the main characteristics of how to hook up a bridge amplifier. So you can look more into bridge amplifier circuits if you are interested into it, but now you have an idea of how a bridge amplifier is, how an how two op amps are connected in a bridge configuration. Okay, so we are back at the volume control potentiometer, which we saw earlier when we discussed the power supply section. So now let's actually take a look at the volume control part of this thing. So basically, pin D is a rotor, and pin C is connected to ground, and pin E goes to the audio amplifier. So how we control the volume is that so basically there's a resistive track inside this like this, and rotating the knob changes the position of the shaft. So it could be here or it could be pointing here. So basically the closer it is to ground, then the more of the signal is shorted to ground, so we have less output over here. So that is basically how the volume control works. So if you wanted a high volume, you would have this shaft, you would have the rotor all the way up, and so basically it's a variable voltage divider. You can think of it as a variable voltage divider. Okay, so let's see how the headphone jack also works as an on-off switch or a disable switch for the speaker once the headphones are plugged in. So basically, the speakers are connected across these 2 points. The speaker voice coil. One side of the voice coil is connected here, and the other side is connected to this island over here in the middle. So when nothing is plugged in, these two pins and these two pins are shorted. And this trace over here, this it's hard to see the picture, but this is all one trace, and this is a separate trace. So this trace is connected to one of the IC outputs, and that output is shorted here to this island from both the sides. It doesn't really matter, but both of the sides of this trace are shorted to this island over here. That means that the speaker is completely in circuit and we are getting an output from the speaker. But now if we connect our headphones, the internal switch of the in the headphone jack, what it does, it breaks the contact between here and here and here and here. So now this island isn't connected to the output in any way. So only one side of the speaker is in circuit, therefore the speaker is disabled. But we do have an output going to both the channels of the headphones plug. That is because this this output from the amplifier is going here to one of the channels, uh, one of the pins of the headphone jack, and to the other pin of the headphone jack. So the same signal is fed to uh, both the channels of the headphone plug, and this is the common. The common is just the other side, which is goes to the other output of the IC. So it's pretty simple actually. We just connecting this to common and connecting both of these to the same point to one of the IC's output pins. Okay, so here's the board with the power supply completed like we did in the last section, and now also the completed audio amplifier section has been added. You can attach your speaker or any 8 ohm speaker will do. You can attach it to test the functioning of the audio amplifier stage. As for the input, you could probably apply it at either the volume control or maybe the AM/FM selector switch. And yeah, so now we're ready to do some tests on the audio amplifier. So the first thing we do with IC circuits normally is check the voltages at the pins. We make sure we have VCC 3 volts at the VCC pin or the V plus pin, whatever you want to call it. We make sure we have nothing at the ground pin. We make sure that we have no DC voltage at the speaker output, because that can be catastrophic. It can destroy your speaker. And once we're sure that the voltages seem okay, we are ready to feed an audio signal at the volume control, or like I said before, the AM/FM switch. And then we can check to see if we have a clean undistorted output with a speaker or an oscilloscope. Now, some of optional fun you can do with this, if you have the equipment, is you can calculate the max unclipped output power. You can figure out the output voltage at the output voltage at which the output starts to clip using an oscilloscope, where it just starts to distort, and back out a little bit. Check out the voltage that you have, the peak to peak voltage, and you would have to convert it to RMS, and then you can use the power formula. So you could use the formula, which is where's the pen? Power is equal to voltage, E for voltage. It's a convention to use E for voltage, because E could stand for electromotive force, which is the same thing. So power is equal to voltage squared divided by resistance. So you could here resistance would be the impedance of the speaker. So you could use this to uh, work out what is the output power here. It's not going to be much, maybe under the under 1 watt, something under 1 watt, maybe well under 1 watt. I should check it myself. I might do that, but this I think if you want to play around with this, this is one of the things you could do. You could also check the frequency response of the circuit. Again, you would need the equipment for this. You would need a function generator, and you would need something that could do a FFT, fast Fourier transform, at the output, or you could do this the old school way. You could not the old school way, but the hard way, let's say. You could feed in uh, different frequencies at the input, and change the frequency in steps of, let's say, 100 hertz or something like that, and then plot. If you're crazy enough, then you could make a plot of the frequency response if you wanted to. But that's about wraps it for the audio amplifier. And if you can think about any other fun stuff to do at this stage, please let me know in the comments. But for now, let's move on to building the AM section. Okay, so now let's start with the analysis of the AM receiver section. Now this is a very old school type of AM receiver section, even though it uses an IC, and you'll soon understand why I call it an old school kind of AM receiver. Now let's move on to the schematic. So here's a radio schematic with the AM section identified. Again, let's isolate this so we can just focus on the AM section and redraw it in a more traditional and familiar way, the way you'd expect to see it in a textbook. Not these schematics of these kits are drawn to make it fit into a certain size, so they draw it in a way that doesn't make it easy to figure out what exactly is happening. But before we see the redrawn schematic, I want to show you something first. Okay, so this is a simple one transistor AM receiver circuit. This is the sort of circuit that was published in many hobbyist publications back in the 1960s. This is by no means a professional quality circuit, but it, it can work surprisingly well, and it was quite common among hobbyists back in the day. So let's take a look at this, and once we get back to the CF210SP, you'll see why this is relevant. So basically what we have here is our antenna, a tuned circuit. So the tuned circuit consists of a ferrite rod on which a coil is bound, and our variable capacitor is connected across that, forming an LC tuned circuit. We'll talk about more on that a little bit later. And that basically that's the the antenna picks up this the station that the tuned circuit is tuned to, and it is rectified by this diode. So it cuts off, as you saw earlier, the AM modulated signal kind of looks like this, right? It it But we don't need the lower part. We only need one part of it. So that's why we have to use this diode. This is a detector diode, and here the detection is actually happening before the signal is amplified. So basically this is the actual radio receiver part of this, and this is just an audio amplifier. Okay, so the radio frequency signal isn't actually amplified. So in a professional quality radio receiver like the super heterodyne type, which we will talk to later once we get to the FM section, we would normally have the incoming RF signal is amplified a little bit, either that or it is converted to another high frequency signal, intermediate frequency, and that is amplified. But in a simple receiver like this, it is just directly, it's basically detected and converted to audio right here. We get our audio output here, and that is amplified, and it's fed to the amplified version appears at the collector of this transistor. This is a bias resistor, and a crystal earpiece is connected across the load. This circuit would not work with a regular 8 ohm speaker. We need a high impedance crystal earpiece for this to work. And as you will see, the circuit configuration of the TA7642, if I've said the right number, the IC that we are using, is pretty similar to this, except that we don't need a diode because the rectification takes place inside the IC, and the IC actually contains a bunch of transistors and has a bunch of amplifier stages like this. So in theory we can build a very simple old school circuit like this, but at least theoretically get much better performance out of it using this IC, and that is what makes it pretty cool. So let's take a look at the IC in more detail. Okay, so here we have the data sheet of the TA7642. Now this is a very sparse data sheet. It doesn't really give us much information about anything, but we can see an internal circuit here, and it is basically what it is. It's just we have a long tail pair input section, which is basically just a high input impedance, like an impedance matching amplifier thingy. So basically that prevents loading on the tuned circuit. So we don't need a tapped coil like we saw on the old school one transistor circuit. And then we have a bunch of amplifier stages. I believe they amplify the RF signal before it is detected, but the detection, there isn't actually a detection, a diode for detection as we saw in the old school circuit. But if you think about it, the base emitter voltage drops. So when the RF signal has been stepped up enough, it will the base emitter the diode, the junction, the base emitter junction of this last transistor is what I believe actually does the rectifying. So in theory this should perform much better than that one transistor circuit with the actual circuit looking pretty similar, but obviously we have this one thing that looks like a transistor, but we have a whole bunch of transistors inside. So it sounds like it would be a fun IC, but unfortunately in my experience with it, it hasn't always performed much better than just a single transistor. So maybe I'm using it wrong, I don't know, but that's my experience with it. So anyway, if you want to learn more about this chip, I recommend this website, peterwiss.com slash this URL. I'll put this in the description, and he goes into a lot of detail about this chip, and he shows a very amazingly built project using an old school breadboard, a real breadboard construction. And I recommend you go through his website, and there's a lot of good stuff about this chip and other old school radio circuits on there. So yeah, so let's go back to the data sheet, and let's scroll down to the application circuit. So what's cool about this, if you look at it, it's almost exactly the same if you think of this as a transistor, and you can think of that as one single transistor. It's pretty similar to that one transistor old school circuit we saw. Of course, they have added here some two more transistors for some audio amplification to drive a 32 ohm speakers, but that is not used in our CF210SP kit. We are feeding the output from here directly to the audio amplifier. So let's go back to the CF210SP application of this TA7642 chip. Okay, so here is the TA7642 application as used in the CF210SP uh, radio kit that we are building. So let's take a closer look at how it works. So at pin 2, the input of the chip, we have an inductor and a capacitor forming an LC tuned circuit. The inductor is a fixed one, fixed for all practical purposes. It can be adjusted slightly by changing the position of the coil on the ferrite rod on which it is mounted, and across that we have the variable capacitor, which is adjustable from 17 to 165 picofarads. That is what I've measured, and this is what is connected to the tuning dial or the tuning knob of the radio. So when we tune to a different station, we are basically varying this capacitance value. And by varying this capacitance, or technically by varying either the capacitance or the inductance, we are changing the resonant frequency of this LC tuned circuit. So the resonant frequency is the frequency at which this LC tuned circuit is most sensitive, and that is the frequency that will be picked up by this receiver. And this also acts as an antenna. The ferrite rod and the coil also acts as an antenna, so we don't need an external antenna, although we could improve performance by attaching a long wire antenna to it. So basically the frequency to which this LC tuned circuit is tuned to is what is fed to the input of this IC. Now the frequency at which this tune circuit resonates is determined by the formula 1 divided by 2 pi, and okay, just imagine that is the pi symbol, times the square root of inductance, which is L, times capacitance. Now we can work this out at assuming our inductance is fixed at 688 microhenry, when the variable capacitor is set to 165 picofarad, our resonant frequency will be around 472 kilohertz. So which is below the AM, just little bit below the AM broadcast band. Obviously, once these values are approximate and once it is assembled, we have to tune the tracking by adjusting the trimmer or the position of this coil to get the frequency range that we require. But that is approximately right, if you ask me. And then once you reduce the capacitance, uh, set the variable capacitance to its lowest value, 17 picofarad, then our resonant frequency using the same formula will be around 1471 kilohertz, which is a little bit below. I mean, for practical purposes, it's almost at the top end of the AM broadcast band. And again, these are approximate figures, but you can see that this makes sense, right? You're basically almost having the entire AM broadcast band coverage. And so basically, by reducing either inductance or capacitance, you tune to a higher frequency. But in practical cases, it is, well, in most cases, it is almost always in a tuned circuit, almost always the capacitance that is varied. Actually, the inductance in certain radio circuits, in particularly in old car radios, you will find that the capacitance is not varied, and it's a fixed capacitance, but this inductance is varied. It's called slug tuning. They vary the inductance by basically moving the core in and out of the coil. But that's a different story. So basically that's that's how this tuned circuit works, and this is the most important part of an analog radio receiver. Now the VCC is fed to the pin, to the IC at pin 3 through this resistor, through R8. This also probably acting as some sort of load resistor if you're thinking of this as a transistor circuit, which it's not, but for the sake of understanding, I mean, some of you might lynch me for this, but it's a approximation that works. So the actual circuit has over here, it has two capacitors in parallel. But when you have two capacitors in parallel, it the capacitances add up. So basically it's acting as one filter capacitor. They probably did that because one value was cheaper than the other or something like that. So this is basically to filter out the power supply. It also could be some sort of low pass filter for the output. And this resistor right here, R10, acts as a negative feedback, and together with this capacitor it also helps the IC to compensate for sudden changes in signal strength. So if you're, for example, you're driving along and you get to a spot where you have stronger reception, suddenly you have much louder volume out. So this is what prevents the volume from changing suddenly, and that is called AGC, automatic gain control. So that is the cool feature of this IC. Like obviously the simple old school circuit we saw earlier does not have this. Okay, so here are the components of the LC tuned circuits in reality. So on the top over here, we have the AM ferrite coil antenna or the ferrite rod antenna. So the core is made out of ferrite, which is uh, basically powdered iron, and on wrapped around that we have the coil. And together with this core, this coil has an inductance of 688 microhenries as we discussed on the previous slide, and this is the variable capacitor. We look at the connections on the back side in more detail in the next slide, but for now keep in mind that this actually contains two variable capacitors. Actually there are a couple of different ways you can connect these, but generally they are made for AM FM radios in mind. So there is one set of connections that can give you uh, a much lower capacitance value for use with FM, and then little bit higher values for AM. So here's the back of the tuning capacitor or the tuning condenser like they used to call it in the old days. So as you can see, the tuning dial has been attached to the shaft on the front, and here we can see the connections. Right here we have notice you can notice the tab. We have a smaller tab on one side, so that is how you orient this on the PCB. But going back to the connections, here we have across here and here the connection for the AM side of the capacitor, and that gives us the tuning range of around 15 to 165 picofarad, and that range can be adjusted a little bit with this trimmer. So once this is assembled, we have to use this trimmer to ensure first that the right station appears at the right point on the dial. Once we attach the front panel, the tuning dial with the indications of the stations, and also together with we'll have to adjust this together with the position of the coil on the ferrite rod to make sure the tracking and the broadcast band coverage is right. And also we have the FM side of it over here, across here and here, which has a much lower capacitance range of 13 to 36 picofarads, and we have a trimmer for that over here. Okay, so that was a quick demonstration of the assembled AM section picking up the local AM radio station and showing us some news in Marathi. This is pretty much the only station I get on AM at my apartment, and that too this is with a long wire antenna attached. So in the big cities these days, because of all the towers and the interference from the fluorescent lights and switching power supplies and such, AM reception is generally very poor. But with a with a good radio, I can actually pick up the stations and some shortwave stations without an external antenna. But with this particular one, as expected from this IC, I was not able to get it to work indoors. Maybe it will work well outdoors with a with just a ferrite rod. I had to use the long wire antenna clipped onto it. But I have to say that, yeah, it really sucks living in a big city if you're into vintage radios. I love visiting the countryside because basically the AM band really comes alive and shortwave too really comes alive. In fact, I do work on some of my radio projects when I'm staying at my family's farmhouse. So once that's all assembled, you can again check the voltages at the IC pins. There's only 3 pins here, but you could check them anyway as a matter of habit. Of course, the output pin will have a DC offset to it because the, the output and the VCC pins are shared on this IC. And then you could test it with a signal generator. If you have a signal generator which can do AM modulation, so you could check how it tracks the broadcast band. You could start off just to see if it works with a frequency somewhere in the middle, and you can try tuning to your your signal generator. Basically, you can, I suggest, loosely coupling it to the ferrite rod antenna. So basically, you wrap the output lead from your signal generator around the ferrite rod, but you don't actually connect it to your PCB in any way. So yeah, and or if you don't have access to a signal generator, or or one that can do AM modulation, you can try tuning to a station. If you do get AM reception at your location, you can try setting it, checking it that way. And if you don't get anything, you definitely should try an external antenna. A couple of feet of wires can breathe some life into a dead receiver, especially if you live in a city. And optionally, if you really want to geek out about it and you want to learn more about aligning radios, obviously there's not much alignment to be done here. This is not a super heterodyne radio, but you could do something like setting the tracking. You could put a test signal at 535, and it should appear towards the low end of the dial, and then you could put a higher frequency. You could put 1605 and see where it appears, and then you could mess with the variable, the trimmer on the capacitor, and the position of the coil on the ferrite rod to make sure you're covering the band correctly. And yeah, so that's about wraps it up for the EM section of the CF210 CP radio kit. All right, so we are finally here at the fourth part, the FM receiver section. For many of you, this is probably the most exciting part of this build. Uh, Maybe you live in a city where you only can really get FM reception like me, which is unfortunate because AM and shortwave is really cool in my opinion. Anyway, a little Steely Dan reference for those of you who have good taste in music, and that's it. Let's get on with it. So, most commercially available radios and most good radios, at least the analog ones, used a type of circuit called a super heterodyne radio receiver circuit. And this applies to both AM and FM receivers, but the AM section of this particular kit does not, it uses a TRF as opposed to a super heterodyne receiver circuit, which has much worse performance. It's much simpler, and it's more of a novelty kind of circuit as opposed to a serious radio. But fortunately, the FM section over here, that is a super heterodyne receiver. And so let's talk about how a super heterodyne receiver, the basic principles of how it works before we take an actual look at the IC and of the circuit in the radio kit. So as with the tuned radio frequency type, we have a tuned input. Sometimes the input is not tuned as it is in the kit we are building, but we could have an LC circuit here at the input, and also we have what's called a local oscillator. And basically there'll be another LC tuned circuit here, and these both of these tuned circuits will be ganged together so that and adjusted so that this circuit, the oscillator circuit, tracks to it's usually in a case of FM super heterodyne receivers, it's 10.7 megahertz above whatever frequency we have coming in over here, and that is fed through an RF amplifier. Sometimes you have that, sometimes you don't, to a stage called the mixer. Now what happens at the mixer? You are getting here the station that you're picking up at the antenna over here, and you are suppose that let's just say it is 100 megahertz, and over here we have you have 100 plus 10.7 megahertz, and both of those frequencies mix over here, and the output that we get from this mixer will be having a couple of different outputs, but the one that we want is it'll be uh, basically a signal which is at 10.7 megahertz, that will be called the IF, intermediate frequency. So we'll have a 10.7 megahertz output here, but that output will retain of whatever the modulation of whatever we had at the input. So basically, what we are doing here is we are converting this signal, no matter what frequency this is, whether it is 101, 100 and whatever it is, it's going to be converted to 10.7 megahertz. Now the advantage of this is, see, it's much easier to build an amplifier that if you think about it, an amplifier is the core building block of a radio receiver. But we're going slightly off track. But uh, it's much easier to build an amplifier that is designed to work with a short range, a narrow range of frequencies rather than a wide range of frequencies. And we can improve selectivity that way, we can improve sensitivity that way. So we have and we could have tuned circuits also between. We always normally we do have tuned circuits that basically select the 10.7 megahertz or whatever the IF frequency is, and reject all other frequencies. And also obviously when we are talking about an FM receiver here, it's this is not going to be it's not going to be tuned very sharply. It's going to allow some deviation of that, but it will make sure that we are only passing frequencies which are centered around 10.7 megahertz. So yes, so having this IF system, having these IF filters, basically allow us to filter out noise, filter out interference from other stations and unwanted rubbish that we don't want basically. So then we amplify and filter this. We can have multiple IF stages. IF stages means I guess amplifiers and filters. So we can have a couple of these stages, and these amplifiers and these filters can be very efficient. They can work very well because they only have to deal with a small range of frequencies, or maybe even just one frequency, and then we demodulate using FM demodulation is much harder and much more complex than um, AM demodulation. You need something like a ratio detector. You can look that up. That is sort of circuit that we need to turn the frequency deviation into amplitude deviation and get an audio signal out of it. So we'll have a demodulator here, and that demodulator will create an audio signal that, as we have discussed before, that is fed to the audio amplifier and that drives the speaker, blah blah blah. But really the main characteristic of a super heterodyne circuit is this front end right here, specifically this local oscillator and this mixer. So basically that is what the heterodyne action really is. We are mixing the frequencies, we're mixing the local oscillator frequency and the incoming frequency to get another frequency which is always at a known it is always at the known IF value. It is always no matter what station you are tuned to, it's always going to be 10.7 megahertz. And that is 10.7 is what's usually used for an FM receiver, and AM receivers are something like 455 kilohertz. Now, super heterodyne receivers, I said there's this tuned circuits after every couple of every amplifier stage, and these tuned circuits use something called an intermediate frequency transformer. So these look something like this. It's a little can with a adjustment on top of that. Now these are quite bulky. I mean, the small ones in transistor radios are, to me, they're quite adorably small, but nowadays everyone's obsessed with miniaturization, so these are considered too big for uh, for a modern compact circuit. Newfangled engineers and a obsession with miniaturization, I guess. So basically, the very latest FM receiver ICs, they try to uh, they try to do away with this. They try to get this selectivity by using some other method of filtering the 10.7 the IF was some other method of basically selecting the IF signal that doesn't require these bulky transformers. Now the chip that we are using in this radio is an early attempt to do this, an early attempt to do away with these bulky IF transformers, bulky and expensive IF transformers. So let's see how they accomplished that. So here's the FM section outlined in the schematic, and it doesn't look anything like that block diagram that we just saw. So you might be wondering, how is this supposed to be a conventional super heterodyne circuit? So let's try to figure that out, and obviously we'll have to turn to our old friend, the datasheet. Okay, so here we are in the TDA7088 datasheet. There's a couple of different versions of the datasheets available for this IC because it was over the years been made by a lot of different manufacturers. This one is by UTC. This chip was originally developed by Philips, and you could also look up the Philips datasheet if you want to. So let's look at how they describe this chip. They say that the circuit contains a frequency locked loop FLL system with an intermediate frequency of about 70 kHz. Selectivity is achieved by active RC filters. So by this what they mean is that instead of by active RC filters, what they mean is that instead of the traditional LC filter in the form of an IFT, intermediate frequency transformer, remember those bulky IFTs I talked about? So that is done away, they have done away with that by using simple RC filters, resistance capacitors filters instead. But for that they had to use a very low IF frequency of 70 kilohertz as opposed to the traditional FM IF frequency of 10.7 megahertz. Now there's a problem with this because the deviation of a FM modulated signal is, is more than 70 kilohertz. So this would cause distortion, right? Because we are not able to reproduce, we are not able to track that entire change of FM deviation, frequency deviation. So what they do to deal with that is they use a frequency locked loop system, the FLL, to basically shift the local oscillator frequency along with the signal. That way, even though our IF is doesn't IF is actually less than the actual deviation of the signal, by tracking the oscillator along with the signal we can still reproduce the entire variation, frequency variation. Okay, so let's see the features that they mentioned. There is a mute circuit in this. So basically that is for muting the output in between stations. So when you're tuning and you're not locked into the station, we have a facility to mute the output, and that is not used in the CF210SP. And there is also a very interesting feature for search tuning. So instead of turning a knob, you can tune into stations by pressing a button for the next or previous station. Again, this is a very interesting thing that they've done, but that is again not used in our current application with the CF210SP. And mechanical tuning, that is how we are doing it, with integrating AFC, that's automatic frequency control. That is kind of like AGC, but here it is, the intention is to keep it locked onto a frequency. So that's kind of an advanced topic, so we won't get into that much. And interestingly, it does say an AM application is supported. Now this is interesting because we are using an AM, we are building an AM FM receiver, but we are not using the AM application as supported by the TDA7088. Instead, AM section is completely separated. I'll show you why they did that. It's to cut down on costs. Okay, so here is an example of the AM application, AM FM application, and interestingly the same chip, the TA7642 is used, but here it is used as an IF amplifier, and the oscillator of the internal oscillator of the TDA7088 is switched between tuned circuits for FM and for AM as well. But I believe the reason they have not done this in our kit is that this would require additional it would require one IF transformer, and so and this also seems like some sort of IF transformer or oscillator transformer, and that would increase the cost and make the radio bulkier itself. So that is why I believe they decided to keep the AM section separate, which is a pity because this is a very interesting circuit, and I would like to try this someday. I don't believe I have never seen an actual application of this AM/FM circuit. So yeah, so we are getting a little bit sidetracked, but what we are trying to do is figure out how this IC relates to the standard block diagram of a FM super heterodyne receiver that we are more familiar with by now. So let's try to work that out. As you can see, this is kind of like a hybrid between a schematic and a block diagram. It's like we have some components they have shown, but it's kind of it's still a little bit confusing, but let's see what we can work out. So we have the input over here, we have a mixer. So here we can see the relation between the standard superhead circuit and this chip, and VCO, that is simply an oscillator. And then we have an amplifier here, which is the output from the mixer is going to this amplifier, and obviously then that means that this is our first IF stage, and this is the component, these external capacitors, they are the filter capacitors for that tuned circuit. Like it was mentioned above, RC filters are used instead of IF transformers. Then we have a limiter. So limiter is basically it, since you know at this point the signal hasn't been demodulated yet, but we only care about the frequency modulation. So what this does is it cuts off the peaks of the top and bottom peaks of the signal to get rid of any noise induced by unintentional modulation, unintentional variation of the amplitude. So we have a nice simple frequency modulated signal without any variation of the amplitude, and then it gets demodulated here. So yeah, and then we have a loop filter. This is all related to the feedback loop that we talked about to shift the oscillator frequency, and we have some circuitry for the mute function that we are not using, the search tuning that we are not using, and actually you can see in this example in the data sheet, they are using electronic tuning which uses a variable capacitance diode instead of a variable capacitor. So basically the capacitance of this diode, it varies based on the voltage that is across it, and there is a system used inside the search tuning circuitry of the IC that we can use to charge a capacitor, a fixed capacitor, and kind of alter the voltage across this, but we're not really concerned with that right now. Now there's another kit available that uses this IC. It's a little bit more expensive kit. It's by Elenco. They have some great kits out there. That is the FM88K kit, and they in their instructions, their kits are much more well documented than what we are working with, and they have a nice simplified block diagram here. It's still not organized in a very straightforward way as you would expect to see it, but it's kind of helpful. So I'll put this link in the description. Now the TDA7088 is based on a chip called the TDA7000. The TDA7000 was the first version of the chip, and it basically works on the same concept, but it's lacking a few of the additional features of the TDA7088, and I find that there's much more information available about the TDA7000. So I suggest you this page on cool386.com that goes into some brief details about the background about this chip. I'll link this as well so you can go through this. You can also go through this document, which is the application notes for the TDA7000, which they have called the AN192 over here. This goes into much more detail about things like the phase lock loop and the frequency deviation and things like that, and the active IF filters. So this is also very, if you want to go into a little bit more depth, you can read this. And another thing that I will link to is this old publication right here, which has a nice article about the TDA7000 radio. They go into functioning of the circuit, and they explain in much more detail than I can about the low IF and the overall functioning with how the demodulation is done and things like that. But now let's jump back into our CF210SP and let's see how the this chip is implemented over there. Okay, so here is a hybrid block diagram and schematic of the TDA7088 as used in the radio that we are building. Now, I've drawn this in a way that it's organized in a, in a structure more similar to how you would draw a block diagram of a FM superheterodyne receiver. So let's start with pins 11 and 12 because this is where the input, the antenna is connected. The antenna input comes in over here and we have a broadly tuned LC circuit. By broadly tuned, I mean is that it's not very sharply tuned. This is accomplished through the internal resistance between pins 11 and 12. So basically, it probably tuned somewhere in the middle of the FM band. So it attenuates frequencies that are above, way above, and way below that, but it doesn't tune into any one specific station as such. So this is not an adjustable, this is a fixed tune circuit. There is no way to vary this when you're using the radio. And if you wanted to analyze this in more detail, what you could do is you first would have to measure the inductance of this, which I was not able to do successfully because it's such a small value and my instruments, my inductance meter that I have is not precise enough for that. But if you do have a precise inductance meter, you could measure that and then you could treat this whole thing as a, you could calculate first the resonance frequency of these two capacitors. You would have to figure out if these are in series or parallel, and then you would have to combine them accordingly and then figure out the resonant frequency. You could also treat all of these capacitors as a frequency dependent voltage divider and find out kind of how it reacts at various frequency, what the reactances are and so on. Now here at pin 5 is how we actually tune to a station in this radio. So we have the oscillator tuned circuit which consists of L2, and across L2 is the variable capacitor CA which is in series with this capacitor right here, and uh, parallel to that is this damping resistor. I'm not sure why they would need a damping resistor here, and I couldn't find any information about that. And also this capacitor here. So the total capacitance would be these two in series in parallel with this one. So you would have to calculate this if you wanted to, for example, infer the value of L2. You would have to combine the values of all of these by using the appropriate formulas for capacitors in series and in parallel, and then you would have to infer what this value would have to be in order to get a tuning range in the FM broadcast band. Obviously this has to tune to whatever station we want to listen to plus 70 kilohertz because this is controlling the oscillator. So here we have the mixer. It's getting its input from the RF front end over here and from the oscillator here. So both of these signals, this signal and this signal, are mixed here to create a couple of different outputs, out of which what we care about is the 70 kilohertz IF signal, and that is selected to this filter. This filter selects the 70 kilohertz signal, or the signal centered on 70 kilohertz because this is the frequency modulated signal. The capacitors for this filter is located outside. This is a low pass filter capacitor, and because of this we don't need an intermediate frequency transformer. So this one capacitor is all that we need, and then the filtered output goes to the amplifier. So this filter and this amp together can be considered the first IF stage, and then again it goes to another IF filter, and then it goes to the limiter. So the limiter removes variations of the amplitude of the signal. So we have a nice frequency modulated signal of a steady amplitude because we don't really need the amplitude variation, that is just noise. And then that goes to the demodulator. Demodulator outputs and turns the frequency modulated signal into an audio signal that is fed to an audio amplifier. And this is not an audio power amplifier, it's a sort of a preamp, and that output leaves the chip at pin 2. Now you can see here there is a feedback going from the audio amplifier to the VCO, to the voltage control oscillator, and this feedback is used to vary the oscillator frequency based on the deviation of the audio output. So this is how the IF is, IF is IF is made to track the audio signal variation so that we can cover the entire frequency deviation with a very low IF of just 70 kilohertz. Then the remaining components, we have here a feedback, negative feedback for the IF. This shouldn't be confused with the oscillator feedback. This is nothing to do with shifting out of frequency. This is just for stability. We have our power coming here at pin 4, ground here at this pin 14, and we have the mute circuit which is not used. That is disabled by this resistor and this capacitor, and we also have the surge tuning which is not used, and that is disabled by this resistor. Okay, so here's a look at the variable capacitor again, and like I mentioned earlier, this is the FM section over here, and this is the trimmer for the FM section. So when you tune the oscillator to make sure that the right station appears at the right spot on the tuning dial, you would have to adjust this little trimmer here. Okay, so at first I was not able to get the FM section to pick up any station at all. So after a bit of experimentation, I found out that I had to increase the spacing between the turns of this coil, the oscillator tuning coil L2, to reduce the inductance. So I had to do that to get it, even to pick up any station at all. So I could use the trimmer on the variable capacitor to align the dial. So that was a quick demo of the FM section in operation. So it works okay. It's not amazing by any means. It's got decent. It's fairly sensitive, but the audio quality is far from good. Let's say that. But that's probably due to the really poor quality speaker. I'm actually using a different speaker which is a little bit better than what came with the kit for this test. But yeah, it's a fun little project. It's not meant to sound amazing. So once you have assembled the FM section, you can check the voltages at the pins. As as with all the other sections, you can check if you have too much DC offset at the output. You can check the input. You can check the VCC if you have the correct voltage. You can check ground, and you could also try checking the voltage at DC voltage at the oscillator pin and tuning the radio and seeing if that changes. And then you could all then main way you could test this, because most people are not going to have a frequency signal generator go that can operate in the FM band and that can also do frequency modulation. Mine certainly can't, only goes up to it can do shortwave frequencies, but definitely not FM, and it doesn't have frequency modulation. So you would have to tune it by ear basically. Try to find the station and then try to mess with the trimmer to to get the station, get a strong signal at the right location on the tuning dial. Obviously, you would have to at least assemble the front panel of the radio so you can see the tuning dial. And if you're lucky enough to have a signal generator, then you can do it properly. You can see how it tracks the entire FM band. And also, I suggest you can also try to infer the inductance of L2, so you can put your knowledge about tune circuits and the formulas. You can research the formulas for series and parallel capacitance, and you could use that to work out the resonant. Since you already roughly know the resonant frequency range, you can use that to estimate the inductance value of N2, that oscillator coil. Now, once you're happy that that the circuit is working well enough, you double check all your solder connections, everything. You'll have to assemble it into the case. And for me, this was the least fun part of the entire build, because honestly, the molding of the case is not very good. I did have some clearance issues with the tuning dial, particularly. It was a bit of a pain getting everything to fit in and then have the case, the back part of the case sit flush. But yeah, it's possible in the end. You can watch some of the other videos or about this radio to see, focus more on the assembly part, because that is not really my goal with this video. And yeah, there is a very nice mechanism for the tuning indicator. So basically, this this little plastic piece that fits onto the wheel, the tuning wheel, and then it threads into this channel. So yeah, that's a pretty clever way to have this tuning indicator. Okay, so that about wraps it up for this video. As you can see, we have ended up with a cute little AM/FM receiver which works okay. It's quite adorable. It's a pocket-sized receiver, and I hope you learned a lot in the process of building it. If you did follow along in building, I know I sure did learn a lot, and also I didn't talk about the assembly, but it was pretty good practice to assemble it considering that the FM chip is a surface mount chip. So it was good introduction to surface mount soldering as well. And if you enjoyed this, and please like, comment, and subscribe, and all that good stuff that you normally supposed to say and ask the viewers to do. And you can also follow me on Instagram. My handle is at underscore electro idiot. So that's underscore electro idiot. I post much more frequently there. And you could also follow my Facebook page, Electro Idiot, to stay update. And if there is sufficient interest, I'd like to do some more videos on the more advanced radio kits like the HX108, the discrete super heterodyne AM receiver kit. That's my favorite one. So yeah, let me know what you thought about this video, and I hope you learned some.